Welcome back in our channel. Today we will have a applied example about second order homogeneous constant coefficients differential equations from electrical engineering. We have a system RLC, resistance, inductance, capacitance. And here this is the source, so at t equals 0 we disconnect the circuit, and then the system will work depending on the saved energy in L and C. In L, the energy is saved as in the magnetic field, and C in electric field through charges. And R will dissipate the energy as a heat. So how to find the differential equation for this parallel RLC for this system? First, we use Kirchhoff's currents law in this node. We have three currents, one come to R and one IL, and then the third current IC. So we have a summation of I's equals 0. The current to resistance will be V over R from Ohm's law, plus the current in the inductor will be 1 over L integration from time equals 0 to t V dt plus I naught, the initial current, plus the voltage drop across the capacitor will be C dV over dt equals 0. This is equation 1. So what we divide this equation by C and derive it again with respect to time t. So we got this and we rearrange the equation. We got this differential equation, which is second order homogeneous, because this is 0, the right hand side is 0, and constant coefficients. 1 over RC is constant, also 1 over LC. Then we have alpha equal 1 over 2 RC. It's called Nipper frequency, and omega naught 1 over root square of LC, resonant frequency. They are both, their units are radian over second, radians per second. This is our differential equations. We find the characteristic equation lambda square plus 2 alpha lambda plus omega square omega naught square equals 0. Then the roots, this is the formula of the roots. We have, this is lambda 1 and this is lambda 2. We have three cases depending on alpha and omega naught. And for every case, we have a solution. The first case, when alpha square is bigger than, when alpha square is bigger than omega square, we will have two different roots. They are real numbers roots and different in values. And the solution for this type of roots will be this one, and it's called overdamping. The second case, when alpha square equal omega naught square, and in this case this term will be 0, so we will have two equal roots, lambda 1 equal lambda 2, and in this case the solution will be this. We just put t here, and this is the constants A and B. This is A and B, and we find them from our initial condition. The third case, when lambda square less than omega naught squared. And we will get complex conjugate roots. Lambda 1 and 2 equal A plus minus Bj. And this is the solution for this case. And this case is called under damping. The first one over, and this is critical. We move from the first to the second. And the third is under damping. And here we have an example with numbers. We kept the inductor and the capacitor the same value, but we changed with the resistance to see the values of alpha and omega naught. The solution here, alpha, we find alpha, which is 26 for the first case, for this resistance, 1.923 ohm. And we found omega equal 10. So here alpha is bigger than omega naught. And we use the first case. This is the roots, lambda 1 equal minus 2, and lambda 2 equal minus 50. This is the solution. We use the initial condition here. V at time equals 0, we have 5 volts, and the current's 0. So here we put 5, and then every t we put 0. So the first equation, A plus B equal 5. And then we have summation of currents equals 0, Kirchhoff's law. And so this is the current, IR minus IL minus IC equals 0. And the current through resistance will be V over R. And the current through the inductance is 0. And here's the current through the capacitor, dV over dt at time equals 0. We go back to our formula, this one, and we derive it to respect to time to find this one. From this equation. And we got the second equation, minus 2a plus minus 50b equal minus 260. This is 2. We solve 1 and 2 to find b and a. And here we found a equal 0.2083 and b equal 5.208. And this is the form we plug the constants a and b, and this is our solution. The second case, when lambda 1 equal lambda 2, because alpha and omega naught are equals, so this is our formula of solution. Remember, just we add t here. It's the same, but here t. And we put the alpha, which is minus 10 t. Then how to find how to find a and b from our initial condition, which is v at time equals 0 equal 5. Then because here is t0, so this term will be cancelled, and we got a equal 5. The second equation, we got summation of currents equals 0, Kirchhoff's current law, the same as we did here, and we find dV over dt at time equals 0. But just remember, because here we have a product rule, because we have t multiplied by e to the power minus 10t. So this is the second equation, minus 100 equal minus 10a plus b. Then we plug a which is equal 5, we got b equal minus 50. And this is our solution. This is a5 and this is b minus 50. In this third case, when alpha square less than omega naught square, the system is called underdamped. And we will have two complex numbers, and our solution will be in this form. Again, we find the constant a and b from our initial condition. So a equal 5, and again the summation of currents equals 0. Kirchhoff's current law equals 0, and then we find dv over dt from this equation. Again, we use the product rule when we derive the equation. And here. So the second equation we got minus 80 equal minus 8a plus 6b. We know a is 5, and this is our final solution. V of t, we just put the a5 and the b is 6.667. Thank you for watching my video. In the next example, we will have this same system RLC, but in series, to find the differential equation for the system RLC series circuits. Thank you very much, and see you in the next video.